So, what we mean by true weight is the weight that a person would have if they were standing on the surface of the earth. That's what we mean by true weight. I don't like the word true here because true implies that there's some inherent weight that that no matter where we are in the universe, that's our weight. And that's not what it means. So, I don't have the power to change things, but if I did, if I were king of the physics world, I would say, everybody, let's start using the following terminology. What is your earth weight? And what is your apparent weight? Are you with me on that? That true weight is what we're calling your weight on earth. And true weight, we talked about this on that last day, true weight is really just the force due to gravity acting on you in the gravitational field. And I'm going to assume that we're always talking about Earth, okay? In which case the gravitational field strength would be 9.81 newtons per kilogram. What is the apparent weight? Well, the apparent weight is what we experience. It's our experienced weight. And this idea that I'm going to talk about right now, again, I'm not going to go slow here, even though we've talked about it, because this is an important idea moving forward into the next unit, is that we tend to experience forces as being opposite to the direction they are actually applied. So if you're in the passenger seat of my vehicle and we're taking a trip somewhere and Bullwinkle, a moose, runs out in front of the vehicle and I'm doing 100 kilometers per hour and I lock my brakes, you feel forced forward, don't you? You are not forced forward. What's actually happening is you continue to move forward and the seat belt, you're pushed against the seat belt, yes? But what you feel is the seat belt being pushed against you, so you feel pushed backwards. You're deceived into thinking you're being pushed forward, but the force you're feeling is a force on you backwards. When we finally stop the vehicle and get going again, and I pull out onto the highway and I forgot to shoulder check, and there's a big truck coming up in that lane, I hit the gas. And what I'm doing is I'm pushing the car and the seat that you're in forward, and you feel pushed backwards. Yes? These are all things you've experienced. Maybe not a terrifying ride like I'm describing, but it's something that you're familiar with. On the other hand, as I'm driving down the highway, and I admit I'm not describing very good driving skills here, and I'm doing 110 kilometers per hour, and there's a curve coming up, and it says slow to 80, and I'm not paying attention. If I take that curve at a high rate of speed, you feel forced to the outside of the curve, don't you? But you're not. You continue to want to move in a continuous straight line direction, and the car is pushing against you. And what you're feeling is the car pushing you towards the center of the curve, but you experience it as a force towards the outside of the curve. So, when I talk about your experienced weight, the reason why I feel like I have weight right now, and this is a bizarre idea, but just follow the logic of the three scenarios I've given you, the reason I feel a weight is because the earth is pushing against my feet. And it is. I'm attracted to the earth. We push against each other. That's why I feel a weight. If somehow, who's the Greek god who could move the earth? Zeus, maybe. Got under the earth and accelerated the earth upward, I would feel more force against my feet, wouldn't I? Well, that experienced weight really then is the following. It's the applied force upward. That's what apparent weight is. It's the force that I experience against my feet, which is the force that something is pushing upwards on my feet with. So, what does that mean? It means that when I've kind of explained all of this. It means that if I were in a situation where my apparent weight were greater, that would mean there would be a greater force against my feet than the normal force of gravity, which would mean the elevator in this case would have to be accelerating up. Essentially, everybody, if you have this situation where you have a force of gravity down and an applied force up that's greater, then your apparent weight will be greater. This is the applied force. This is what I'm going to call your earth weight or true weight. This is your apparent weight. The APP in red doesn't stand for apparent, it stands for applied. But we lucked out because applied and apparent both start with APP. This is what we're calling in this lesson true weight. So how could this happen? The only way it could happen is if the acceleration is upward, because there's more force up than down. Is this coming back to you now? On the other hand, different elevator, it doesn't matter. If you have that true kind of earth weight and you get on a different elevator, and for whatever reason you don't experience this earth weight, you experience less, and again, that arrow up is an apparent weight. It's what is going to be pushing against my feet, so I'll be deceived into feeling that I'm pulled down with that amount. It's tricky. This will be your apparent weight. This is your true earth weight. Do I need to write apparent and true here again? You get my drift, right? But you see that in this vector diagram, my apparent weight, which is the applied force, is smaller than my true weight. So what would I experience? I'd feel lighter. I would feel lighter. And this would mean that there is an acceleration down. How would an elevator be moving if your apparent weight was your normal weight? Well, the only way for that to happen, the only way for this apparent weight, which is the applied force, to be equal in magnitude to the true earth weight would be if the forces were equal in magnitude, which means zero acceleration. So the elevator can just be stationary or it can be moving but at a constant speed. And given that the question said the elevator is moving, we can just say this and cover all bases. Yeah? Okay. So now this is something that I didn't go, see, on a Friday I think I was kind of trying to rush to maybe fit the lesson in. So I'm going a little bit slower here. There's two kind of ways to do this. I'm not going to go through number 2 again, other than to say your apparent weight is what you experience, which is the applied force upwards on your feet. And the applied force upwards on your feet depends on your acceleration and what direction you're accelerating in, or if you're accelerating. There's two ways to answer a question like number 1A. Let me get rid of these. And to be fair or honest, the first way I'm going to show you is, I think, the simplest, but it's just kind of an intuitive thing. If a rocket is accelerating up, if an elevator is accelerating up, will your apparent weight be more or less than your true weight? So I can tell right away by the looks on some of your faces that maybe this method isn't the simplest for some of you. So let's do it the other way first, which is the physically correct way to do it, and then I'll explain the shortcut, which is what I do. If the rocket is accelerating up, then the scale that this astronaut is standing on is being pushed up against your feet. There is a force of the whole rocket that kind of gets transferred from the rocket to the scale to your feet to your experience in your brain. And that's the applied force. This is F applied. There is also a, again, true earth weight. I'm going to call it Fg. My question now is, once we've drawn that diagram, how is it we know that the force upward is more than the force downward? Ephraim, you said it, but I just want you to say it a little louder. The acceleration is up, so there's a net force up, which means there's more force upwards than there is downward. Okay? But since applied force is your apparent weight, I go back to my question I had before. How many of you see that if you're accelerating up, you weigh more? Okay, we'll come back to that. So how do we solve this problem? This is the goal. This is the answer to the question. We do what we did in so much of this unit. We take our free body diagram and we make an equation out of it. We say F net has a magnitude of ma, which means the mass times the magnitude of the acceleration is equal to the net force, and then we look over here. We look at this diagram, we say, how do you find the net force from this? You take the applied force, its magnitude, and you subtract the earth weight or true weight. Are you guys with me on this? I know it's hard when we've been away for so many days, but so if we solve for the apparent weight, which is the answer to the question, we get, I'm going to write it this way, we get Fg, your true weight, plus ma. The shortcut, the intuitive approach, and maybe I'm explaining it to you this way because it's how it was taught to me forever ago in high school, is to simply say your apparent weight will be more because you're accelerating up, so you're going to take Fg and you're going to add ma to get a bigger force. Okay? And anyway, we did mg, what was it, 100 kilograms? 100 kilograms times 9.81 plus 100 kilograms times 19.6. And just for the sake of the video, I know you have this answer, you probably should have this answer written down. What did we get for 1A? 20, I can't read that though.
I can't either.
You can't either. I mean, it looks really, like it's written really nicely, but.
Probably like 2,941.
2941? Good stuff. Okay, so 2941 newtons. Yes? Okay. Just quickly, this isn't really even something I don't think I would ask you. What is the magnitude of the astronaut's true weight and apparent weight if the rocket is in deep space? I don't like this question. I pulled it from the textbook. Their true weight is their earth weight. And I don't think their earth weight, we can calculate it. Let's calculate their earth weight. It's 100 kilograms times 9.81. For goodness sake, if I turn around and see you guys using a calculator to figure this out, that vein in my forehead is going to pop. It's 981 newtons, yes? Okay. The reason why I don't like this question is this has no relevance to anything going on here. All this is saying is if the astronaut were eating their breakfast at the dinner table in the morning, this would be what they would weigh. It really doesn't matter. It has no bearing on the question. Their apparent weight is the applied force. But the applied force is simply the net force. They're out in what we call deep space, which means they're not beyond the reach of Earth's gravitational field, but they're far enough away that the gravitational field strength is so tiny, who cares? Okay? So this apparent weight, which is the answer to the question, is the net force because it's the only force pushing on the astronaut's feet. So it doesn't matter whether the astronaut is here going that way, or it doesn't matter which way they are moving, or accelerating, I should say. That's the only force, which means it's the net force, which means it's ma. Just so that I can write sensibly here. This is actually the net force, which is found using ma. So all you have to do is take 100 times 19.6 and get 1960, I believe. And that's kind of where we left off here. So this is 100 kilograms times 19.6 newtons per kilogram, which is 1960 newtons. So correct me if I'm wrong. We got that far. Okay. Just take a pause here. I'm inclined to say that our unit exam will be Friday of this week. I know that Mr. Flynn's class is going later on into next week, but I think we have a lot of important things we want to get done in the second unit, and I don't want to cut our time short. And I think we've kind of covered all bases here. So if we say that our exam is Friday, which I am saying, that leaves us 3 days for review. And there's a lot to review here. A lot to review about forces and gravitation in this unit. Number 2, a 75 kilogram person has an apparent weight of 640 newtons while riding in an elevator. So I started off my explanation a few minutes ago about talking about what are the conditions necessary for you to weigh more and what are the conditions necessary for you to weigh less, right? Just to go back and look at this. This is what we're talking about, right? So you need to understand the physics of this in terms of these vector diagrams. That if a person weighs more in their mind, they feel heavier, they are in a situation where whatever they are standing on is accelerating towards their head, also known as up. If you find yourself in a situation where you feel that you weigh less, I'm looking at the middle diagram where the applied force, which is your apparent weight, is smaller in magnitude than your true Earth weight. If you're in that situation, you feel a little bit lighter. You feel as though at that instant in time you could jump higher, and you could. Because as you jump, the elevator is accelerating away from your feet, okay? Then you know that the elevator is accelerating down. And then if you feel normal, there's no acceleration. I don't think we want to dive head first into this problem without knowing whether the elevator is accelerating up or down. There's not enough information for you to look at this and answer that question without doing at least one calculation. This is their apparent weight. This is the applied force up. So if I were to draw my elevator, and you should draw it as well, it's a futuristic round elevator. Let me do that again. If you were to draw your elevator, what we can label on here is that there is a force upward, which is the apparent weight, also known as the applied force of 640 newtons. I want to go back to those 3 diagrams and add something, okay? And you can choose to add it or not. I don't know. We may have even put it in before. I don't think we did. That in this particular case for A, the net force has a magnitude of the apparent force, the applied force, which is your apparent weight minus your true weight. Is everybody with me on how we would get this statement out of that vector diagram? Whereas over here, the net force would have a magnitude equal to the magnitude of your true earth weight minus the magnitude of your apparent weight or applied force. Very tall F there. Is everybody clear on how you would arrive at that statement from the diagram above it? We're back to that thing that I think, Gabrielle, you came up with it first. It's always going to be the magnitude of the bigger minus the magnitude of the smaller opposing, right? Whether it's on a ramp or vertically or on a horizontal surface. And we've talked before about, although these things look as though if you mix them up it shouldn't matter, it does matter. You get different answers. It's not as simple as saying, oh, I subtracted wrong, I'll change the sign in the end. So why am I going through all of this? I'll freeze this up on the screen to your right. We're going through all of this at this point so that we can decide which one to use. And the only way for you to know which one to use, since you're not told which way the elevator accelerates, is to compare the two forces. So how are we going to calculate the opposing force? How are we going to know whether this is representative of the opposing force or this is? Well, we need to calculate that opposing force, which is the true earth weight. We need to calculate mg, the force of gravity. Get rid of that because we don't know it yet. Whoops. So what is the magnitude of the force of gravity, also known as your true earth weight? It's 75 kilograms times 9.81 newtons per kilogram. For some reason this morning I'm on a kick of not putting units. I don't think it really matters. If you want to put units in, put units in. What are we getting to get here? 75 times 9.81, 735.75. And without calculating that, you really, that's not exactly true. You really can't decide which force is bigger until you calculate it. I'm not worried about drawing things to scale here. This is your true earth weight. You know, I would have looked at this question and said, well, the true earth weight's going to be about 750 newtons because it's 75 kilograms, right? So I could have come up with the diagram beforehand because 750 newtons is more than 640. Anyway, now we can answer the question. We can say that the net force, which is MA, I want to back up again. Well, no, I don't need to because I've got it right here on the right-hand screen. I've yet to unfreeze it. You understand that this is MA, right? And I was tempted even when I wrote what I'm pointing at on the side screen to just write MA equals apparent weight minus true weight. So we can do that here. It'll be MA equals, so normally what I would do here is I would write MA equals mg minus apparent weight, but we already have those numbers. Right, we already know what mg is. It's 735.75 newtons. Yeah, I never asked. Did anybody else get that number? Okay. Minus the 640 newtons. And we know this is 75 kilograms, so we just have to take this difference and divide by 75 to get the acceleration. So I'm getting 1.28 meters per second squared. Now, This, what I want to talk about briefly here before we move on, is related directly to your question you had a week ago or 2 weeks ago, whenever it was, about putting the directions into the formulas. You know what I'm talking about, Ephraim? And I said we don't do that, okay? And the acceleration, if we include a vector symbol, is down, which didn't come about from the equation, it comes about from the diagram. Is that okay? So you're going to get a positive out of your work if you set it up this way, no matter which way it's going. We take a look at 3. The same student now has a weight of 900 newtons. Listen, we already know what their force of gravity is. But I'm trying to teach you a little bit of common sense here. You understand that a 75 kilogram person has a true weight of roughly 750 newtons? Because we multiply that by little g, which is very close to 10. So obviously this elevator is accelerating up because the applied force upward is more than their normal force of gravity. The diagram, if you want to show completeness in your notes, the diagram would look like this. You would have that force down of mg and the force upward of the apparent weight. This we've already calculated. Oh man, is it 735.75? Thank you. That's the force due to gravity. I'm not using absolute value signs there because that's the force due to gravity. The arrow is down. And then here we have 900 newtons, and that is the applied force upward, also known as the apparent weight. So this time it's going to be MA equals the bigger upward force minus the smaller downward force. So we can subtract those numbers and divide by 75. I mean, we're doing the exact same set of calculations we did in the previous one. We're taking the bigger minus the smaller force that's opposing it and dividing by the mass. .19 meters per second squared. So once again, we happen to get a positive number. Is that why it's up? No, it's up because when we look at the diagram, the force up is more than the force down. Okay, so this stuff that I'm writing here is an afterthought, and I truly mean that as an afterthought. It's something that I have to think about to decide on. Just the same as over here, when I change this to a negative with a vector symbol and down, I have to think about that. That's what I mean by an afterthought. It's not something that, oh, I better do that, although it is. In addition to that, you have to do it because you're not getting that negative or the positive out of the formula you build. Okay? And that's it. And I'm really struggling here because we have a lot of time left and I don't really believe that there are, well, we'll call it what it is. You've got those 4 problems in your handout on page 43 and then on page 225.